Gold. For centuries, it's been the ultimate symbol of wealth, right? But here's a weird fact about modern gold mining. Most of the gold we pull from the earth today is completely invisible. Yeah, you heard me. It's scattered like microscopic dust inside tons of solid rock. So how in the world do we get it out? Well, the answer involves a pretty toxic chemical, something called a magic sponge, and some seriously clever engineering. Let's get into it.
I mean, think about the challenge here. For every ton of rock we mine, we might only be looking for a few grams of gold. It's like trying to find a needle not in a haystack, but inside an actual mountain. It sounds impossible, but the key is this brilliantly designed chemical process.
So, we're going to follow gold on its incredible journey, and we'll break it down into 4 key stages. First, we'll see how you unlock it and kind of turn it into a liquid. Then, we'll meet the magic carbon sponge that actually catches it. After that, we'll follow it as it's transformed back into solid gold, and finally, we'll look at how this whole process is actually a sustainable cycle.
Okay, so Section 1.
Before any of that chemical wizardry can happen, we first have to free the gold from its rock prison, and that starts with just pure, brute physical force.
Now, before we get to the crushing and grinding, it's really helpful to know what the end goal is. The whole modern process is called carbon-in-leach, or CIL. It's this ingenious method that dissolves the gold and catches it at the exact same time. It's way more efficient than the older 2-step method, mainly because it prevents any of that dissolved gold from getting lost along the way. Now, let's see how we get the rock ready for this. So, how do we begin? It all starts with preparing the ore. First, you've got these massive crushers that just chew up huge rocks into small pebbles. Then, giant ball mills tumble those pebbles around with heavy steel balls, grinding them down into a super fine powder. Finally, we add water to create this thick, muddy mixture that we call a slurry. And when I say fine, I mean really fine. The target is something called 200 mesh, which is actually finer than the flour you have in your kitchen. So why go to all that trouble? Because it's the only way to make sure that every single microscopic particle of gold is exposed, totally ready to be dissolved by what's coming next. And this brings us to the very heart of the process, leaching. This is where the real magic happens. We use a cyanide solution that acts like a chemical key. It literally unlocks the solid gold, dissolving it and turning it into something called a gold complex that's completely soluble in water. So in an instant, the gold has gone from an invisible solid to an invisible liquid. But during this whole critical stage, there is one single number that is an absolute non-negotiable red line. The pH of the entire slurry must, and I mean must, be kept above 10.5. So why is this number so incredibly crucial? Well, there are 2 huge reasons, one for safety and one for efficiency. First, safety. If that pH drops too low, the cyanide will form a deadly hydrogen cyanide gas. Not good. Second, efficiency. Gold just happens to dissolve fastest in a highly alkaline or basic environment. So keeping the pH up is both a literal lifeline and an economic one. Okay, so our gold is now dissolved in this big, soupy mix. We can't see it, we can't touch it. So how do we get it out? This is where the hero of our next chapter makes its grand entrance. Meet activated carbon. This stuff, usually made from coconut shells, is just incredible. Its internal structure is filled with millions of microscopic pores, which gives it a massive surface area. You can basically think of it as a magic sponge that is almost magnetic to that dissolved gold complex we just created. Now, what's really cool is the engineering behind how it's used. The slurry with all the dissolved gold flows in one direction, from the first tank to the last, but the activated carbon flows in the opposite direction. This counter-current design is just genius. It means the freshest, most active carbon always meets the slurry with the lowest gold concentration, which ensures every last possible bit is captured. It's so clever. So just how effective is this whole system? Let's look at the numbers. When the slurry first enters this part of the circuit, the gold concentration is already tiny. We're talking about 10 milligrams per liter. Just keep that number in your head. And by the time it leaves, get this. The concentration plummets to less than 1/100th of a milligram per liter. That is a 99.9% capture rate. It just shows you how powerful that magic sponge and the countercurrent system really are. Practically nothing gets away. So our carbon sponges are now fully loaded up with gold. The big question is, how do we get them to give it back? Well, it's finally time to make our invisible treasure visible for the very first time.
This process is technically called desorption, but honestly, a much better name for it is squeezing the sponge. The gold-loaded carbon gets washed with a hot, high-pressure alkaline cyanide solution. This basically creates an environment the gold complex absolutely hates, forcing it to let go of the carbon and jump back into the liquid solution. And it turns out there's more than one way to squeeze this sponge. As you can see here, some methods like the Zandra process are slower but operate at lower temperatures. High-pressure methods are way faster but more intense. It's all a big balancing act between time, cost, and safety to find that perfect sweet spot. So the gold is now back in a liquid, but this time it's in a highly concentrated solution. The final piece of the puzzle is a bit of chemical magic called electrowinning. We pass an electric current through the solution, which forces those dissolved gold ions to become solid metal again, plating themselves onto steel plates. And now, for the first time in this entire journey, we finally see it, real, solid gold. But the story isn't quite over yet. What about all that used carbon, the magic sponge that's just been squeezed dry? You don't just throw it away. I mean, that would be incredibly wasteful. Instead, it gets a full-on spa treatment. First, an acid wash cleans out any mineral gunk that might be clogging up its pores. Then, it's sent into a kiln and heated to over 600 degrees Celsius to burn off any other contaminants that are hanging on. After this serious deep clean, it's pretty much as good as new. And the results are amazing. This regeneration process restores about 95% of the carbon's original capacity to grab gold. Yeah, a tiny bit needs to be topped up each cycle, but the vast majority is just reused over and over again. It creates this super efficient, economical, and closed-loop system. So when you step back and look at the whole system, from crushing rock all the way to regenerating the carbon, you see it's this incredibly precise, controlled industrial journey. It really is a marvel of physics and chemistry that takes invisible dust locked in stone and turns it into a shining, tangible treasure. And all of this leaves us with one really big question. The core principles of this powerful technology are over a century old, and let's be honest, they rely on toxic chemicals like cyanide. So, what comes next? What will the next generation of cleaner, more efficient gold extraction technology actually look like? Well, that's the challenge for the engineers and the innovators of tomorrow.